So I'm going to take you through pretty quickly a little history of forensics and where we were when I first started and where we are now, and kind of take you up to the point of when we started talking about next-gen sequencing, NGS. And then we'll take a break, and then I'll hand it over to Nick, and he'll get into some of the more technical stuff about NGS itself. So when I started, I think I mentioned a little bit about this. If you go back about 20 years ago, CSI was only in its second season. When I started, it wasn't even a thought in anybody's mind. CSI made forensics extremely popular. And we even have something we call the CSI effect when you went to court. And if you didn't have, forensic scientist or DNA analyst, your jurors were kind of like, where are the technical people? Because they're so used to seeing this stuff now on TV. Great. We had a surge of applicants around that time, I can say. The 9/11 World Trade Center attacks had just happened. To me, this does not seem like it was that long ago. I know to most of you, it was a lifetime ago, but for us, this last 20 years seems to have gone pretty quick. So it feels like that was not a long time ago. Back at that time, our forensic DNA workflow was really pretty fragmented and inefficient and very manual. We did our serology, body fluid ID, it was done first. It was done with, a lot of presumptive tests and confirmatory tests. And you did a lot of looking with your alternate light source and a lot of cutting out stains and putting them, in packages and documentation. So it was very, very manual. In the DNA workflow, we have to quantitate or find out how much DNA is present in a system. In a sample. We do that now with the real-time PCR system, which I'm sure you guys have heard about by now. But back when I started, we did something called QuantiBlot, where we actually put DNA and bound it to a paper and then put fluorescent dyes and had to develop it with film. You compared the size of the band from your sample to a kind of ladder over on the left side of this QuantiBlot picture here. And it was pretty subjective. You decided what it looked most like. So I could look at the top one for the blood and I'd say, that's about 0.6 nanograms in that sample. And the next one I'd say that's 1.2. So it wasn't very exact and it took a long time to do. We also, for analysis, had two different types of software that we had to use. You had to size your DNA before you could type it. Now we have GeneMapper IDX, and it's done all in one software package. But back then, it was very time-consuming, and everything was very manual. We had also, by the way, no automation at this time in the laboratory, and mainly organic extractions. I don't know if you guys have learned about organic extractions or ever done one yourself. They're extremely techniquey and they take a ton of time. YSTRs, when I first started, we weren't even thinking about that. The first YSTR kit hadn't even come out. We, at the time that I started, could not even interpret mixture samples. My first couple of reports went out with a table that would say mix, 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 because the community hadn't really even decided how we were going to look at those samples. Options for handling heavily degraded samples were few. At this point in time, we didn't really know what we could get DNA out of. We came from a time of RFLP where you needed a blood stain the size of a quarter, and now we're moving to PCR-based technologies, and we really, you tried it. And maybe you took your whole sample and tried to get a DNA profile on it. You didn't really know. It was kind of the very early days. Global DNA databases. We didn't have a database in Massachusetts when I first started. Like I said, we weren't even accredited. That all came, in the late 90s and the early 2000s. So I remember we had in our evidence room a whole section with these cases we called U cases. and they were sexual assault kits that had come in without a suspect. They were suspectless cases, and they had their own section of the evidence room because, as you know, DNA is a science of comparison. So if you have nothing to compare it to, what are you going to do with those cases? So they just had their own shelves and sat there until we got a database and we could go back and start working some of those cases. Well, here's a little timeline that takes into account the Thermo Fisher Applied Biosystems brand of products. Back in 1996, we had these kits called blue and green. There were 3 or 4 loci in each of those kits, and you did them separately. You ran stuff on a 310. This is a very early capillary electrophoresis instrument that had 1 capillary on it, so you ran 1 sample at a time. If you set up a plate with 40 samples, you could be there for, a day and a half, 2 days waiting for your data to come off your instrument. In between that and the 5-dye technology, we had kits called Profiler and Cofiler, and those were the kits that were used to do all of our databasing work. Together, they had all of the, I think back then it was 13 CODIS core loci that we were looking for, but there was 2 loci in each kit that were duplicated. You ran 2 separate PCR reactions at a much higher volume than you run now, and you had to compare the overlapping loci to make sure you didn't do sample switches. And you can imagine now you've taken your 1 sample, split it into 2, do 2 PCR reactions, and you're going to run it on your single capillary 310 instrument. After, prior to this, doing your quantiblot, which could take all day to find out how much DNA was even there. In 2000, 2001, we developed the 3100 series of instruments. This is an instrument, it's a multi-capillary instrument that has either 8 or 16 capillaries. So it was a game changer for us. You could suddenly run 8 or 16 samples through your instrument at the same time. And we also came out with the Identifiler series of kits, which contained all of your 13 core CODIS loci in 1 kit. And we had to add another dye. Our blue and green kits were only 1 dye, either blue or green. Profiler and Cofiler were 4 dyes. We needed to add an extra dye to get extra space, extra real estate in the kit. So came out with Identifiler. And then we came out with Identifiler Plus, which was better in the presence of inhibitors and degraded DNA, so that we were starting to get a better handle on what our kits could and could not handle as far as sample types and where we could get successful results. In 2010, we came out with the 3500 series instruments, which is still our gold standard of instruments for a forensic workflow, DNA workflow. This instrument I said the 3130 had 8 or 16. It had 4 or 16 capillaries. 3500 has 8 or 24, and it's got a faster processing time so that your samples are getting through even more quickly. And we came out with 6-dye technology because now that the U.S. was heavily dependent upon our CODIS database, we realized we needed to increase the number of loci in the database so we didn't get any adventitious matches. The last thing you ever want to do is have 2 people match a sample when you put it into your CODIS database. So we increased the number of loci that needed to go into CODIS, and thus we had to come out with another kit, adding another dye for increased real estate so that we could accommodate the 21 now CODIS required loci plus 3 that are recommended. So there's now 24 that we look at. Over that time, we came out with real-time PCR, so goodbye to the good old quantiblot, and real-time PCR started to be the standard for looking at how much DNA you had in a sample, and we were able to introduce new tools through real-time PCR that could also tell you how degraded your sample was, so that you could make downstream judgments on how you wanted to run your DNA. Because by this time, too, we have YSTRs, and we also have mini STRs. Mini STRs are STRs that are just smaller in size, and as you can imagine, when DNA degrades, it gets chopped up into smaller pieces. So if you have a kit that can look at those smaller pieces, then you have a better chance of getting information from that. Well, we weren't done because we knew that there were still samples out there that we couldn't get information for, so we started to look at next generation sequencing. We started really looking for forensics, I'd say more in the 2014-15 timeframe. We did start coming out with stuff earlier than that, But common saying in forensics is that we don't like change. So it takes us a long time to actually adopt what we think is a new technology, but may have been around for years being used by other applications. So we started really looking into NGS more in around 2014, 2015, and coming out with some systems that Nick's going to tell you about. So there's a little mini kind of like walk through where we were and where we are. And like I said, the theme around forensics is we don't like change. But I think from this, in the last 25 years, we've come a long way and we've had a lot of change, and we've become way more efficient and can do things faster and better and get more information from samples. So this just kind of
that as well. All those instruments and all those kits have been approved by the FBI and by all those accreditation bodies and everything. So that's part of the reason why everything takes so long.
Yes, we have to do developmental. We have to create the kits first, do developmental validation, have our lab partners, forensic partners, validate a kit, submit it to NDIS, get approval before you can use it, because everything hinges on that database. And so here's just a little kind of overview of the kits that I just talked about. We're starting with the identifiler. We had mini filer, identifiler direct, which is a direct amplification kit for single source samples where you don't have to do any extraction. So that's really nice. And then our identifiler plus kit that's better with challenging samples. And finally, global filer, which is where we are today. So I know that you guys have gone over this in class, so I'm going to go through pretty quickly, but this is your basic forensic workflow in DNA labs. We collect our sample. You can collect it on swabs. Sometimes it's on a card if it's a known reference sample. We have automation that can actually take punches from cards now and put them in tubes, so you don't have to cut those cards out yourself. Extraction, we offer our prep filer kits, which is a bead-based chemistry. So no longer are people in the lab doing organic extractions. They're able to use automation and new instrumentation to really make it a more efficient extraction and quicker results. Real-time PCR is what we use for quant. For amplification, we have all of our thermal cyclers, and our global filer kit is what we use today. For detection, it's going to be that 3500 or 3500 XL, and it's going to be coupled with that GeneMapper IDX software. This is the way to size and type your DNA all in one software package. And then we also have tools like next-gen sequencing, where we can choose to maybe bypass the traditional workflow, the collection, extraction, quant, amp, and detection analysis, and just move straight into next-gen sequencing, where we know we can't get a result with traditional workflow. For the traditional workflow, it can take quite a long time. It can take, as you see from this slide, 10 to 58 hours. It really depends on the type of sample you have. When you're doing an extraction, if it's a blood stain and you can put it on a robot and use a bead-based kit and get a result, within 2 hours, that's the way you're going to go. But if you've got a sexual assault sample, doing a differential extraction, which is what we do for sexual assault samples when you have sperm cells present, can almost take 2 days sometimes, because you're doing you're separating your epi cells from your sperm cells. So your one sample becomes 2, and then you've got to make sure that you crack open all those cells and get the DNA out. It's a laborious process still to this day, although we are working on ways to make that more automated. Then you've got to, do your quant, your amp, your detection, and then your analysis. Your analysis can also vary in time it takes for a sample, depending on how complex that sample is. If you have a mixture of 4 people, you can imagine when you're looking at your DNA profile, that can take a ton of time to deconvolute, if you can even deconvolute it. Throw in some degradation and maybe inhibition, and that can make your life a lot more difficult. So, you look at these TV shows like CSI, where they're able to get a DNA profile and arrest the guy in 30 minutes. For us in the lab, even processing your sample could take you, up to like 2.5, 3 days, and that would be working constantly on just that sample. And we do a lot of batching in the laboratory to make it more efficient. So you can imagine we have a huge batch of samples that might be complicated, that this is still to this day a time-consuming process, although we've introduced a lot more robotics, but automation doesn't really make things that much quicker in the process. It just frees up your time to do other things, so makes you more efficient, but we still, for casework samples, it's taking quite a bit of time to get this all done. With a direct amplification, which we do for known samples, that cuts that time down a lot because you don't have to do any extraction or quantitation, so we can get that down much quicker. The type of testing that we're doing in the laboratory for the main workflow is going to be the STR testing, the PCR-based testing. And I'm sure you guys have gone over this in class, but the STRs are simple repeated sequences of 2 to 6 base pairs, and they represent about 3% of the human genome. They are random occurrence. They occur on average every 6 to 10 kilobases. They have conserved flanking regions, which make it good for setting up primers and probes. They're also polymorphic. Polymorphic means that they're different between individuals, which is what we're really going for, right? We don't want to be testing DNA that's the same for everybody. We want to look at where we're different. The way that we differ for STRs, these STR regions that we're looking at, is by the number of repeat units. So I may have repeat units that are a 5 and a 6. I got half from my mom, half from my dad, so they're different. And Nick might have, repeat units of 7 and 8 in his DNA, so you can tell the difference between us by using that STR technology. This is just a little show of, in terms of numbers and probabilities. So when you're doing your DNA testing and you're comparing it to somebody, you always have to kind of tell everybody how rare that or how common that DNA profile is. Back when we were using Profiler Plus, we got a number of about 1 in 72 billion, which at that time, coming off of ABO testing, was huge. To us, we were like, there's nobody else that has this DNA profile with these 9 loci. Today, we know that, with closely related siblings, you could probably maybe have 9 loci that are the same. So not as rare as we thought. Today, with the global filer kit, our probabilities are about 7.12 times 10 to the negative 26, and don't ask me what that is. It's a lot of zeros. So more people than there are in the world. Believe it or not, I did get asked once in court if it's more people than there are in the universe. I wasn't really sure how to answer that one. But my guess is probably yes, because I don't think we got human life on other planets. But we, over the years, have not only gotten better, with challenging samples, but we've also added more loci to get more discriminating, so that when we're giving our DNA stats and stuff in court, you can really see the impact of finding somebody's DNA at a crime scene. I mean, these profiles are pretty rare once you get to 24 loci. Here's our CE. This is our 3500 that we all know and love in forensics, that we run on a daily basis with either 8 or 24 capillaries. It's been very refined and really works well with the forensic workflow now. The 310 with the 1 capillary was a little clunky. It wasn't really designed for forensic science, but the 3500 is. And so this is where we're at today, and we run it with our GeneMapper IDX. We're on now actually version 1.6 software, not 1.5 anymore. So we've made a lot of advancements there as well. Just a little reminder for the CE and how that works. The inside of the CE, you've got your DNA and a capillary, and attached to your DNA are fluorescent tags. They move through the capillary window, and there's a laser in your CE that will shine and allow those fluorescent tags to fluoresce. That light comes back into the instrument through a series of mirrors, bounces into a spectrograph, which then separates your dye colors. We've labeled our DNA now with 6 dyes. that then shine onto a CCD camera so that we can take a picture of what that DNA looks like and transfer it to our analysis software. This is a very simple design. I think I got it from my 310 days, but all of our instruments work the same way. We just split our laser beam now into two so that it can shine through the top and the bottom of all capillaries, because as I said, there's 8 or 24. So we want to be able to see across all the capillaries to see the DNA in every single capillary. Again, we have the laser. That's a single excitation solid state laser in our 3500s. It's dually illuminating. Like I said, it goes across all the capillaries from the bottom and the top. And it works the same way as that depiction I just showed you. The light passes through a transmission grating and is projected onto the CCD camera so that it can the data can be moved into your analysis software for review. So this is just showing how your DNA moves through your capillary. It's in there and it's fluorescently tagged, and it's gonna move through polymer, which is the medium that's in the capillary, and it's going to separate itself by size. Smaller particles are going to move faster in this medium than larger ones, and they all have different fluorescent tags on there, so you're able to see what is going across your window and they move in a charged field, so your DNA is going to move through that medium from your anode to your cathode. All right, that was your very fast run through there of your traditional DNA workflow. I hope that's more of a review. If you have questions, just let me know. But that's pretty much the way that we are doing things today, and we have been doing it in a similar manner for the last 20 or 25 years. We've just made improvements with throughput and with how we can work with challenging samples. But we're still not 100% where we want to be. There's a whole bunch of samples that maybe don't work in this traditional workflow. So we've had to look into next generation sequencing. And like I said, Nick's going to tell you a lot more about that, but I just want to give you a little idea here. We probably will take about 50 to 70% of casework samples in a forensic DNA lab through the traditional casework workflow that I just went over with you. So your DNA extraction, your quantification, STR, and analysis. But there's going to be about 20, 30% of samples that if we did this, we wouldn't get a profile. They're either too degraded or too inhibited, that our systems are not sensitive enough to be able to pick up the DNA that's in those samples. So for those samples, we would take them through the NGS workflow. So even though we have this time-tested gold standard for our workflow, we still need an adjunct system or another tool to be able to get the most information that we can out of samples where perhaps the traditional workflow aren't going to give you the results, or maybe they're not going to give you the information that you need. Maybe you get STR results, but you don't get a hit in your database. You don't have anybody to compare it to. We need to find ways to do something with that sample so that maybe we can generate an investigative lead from it where we couldn't before. And NGS is going to allow us to do some of that stuff. With NGS, we have the ability to do mitochondrial DNA sequencing, so we can do a lot more work with missing persons or mass disaster samples where things are very badly degraded. Samples are in really poor shape. We can look for phenotypic SNPs so that we can start thinking about things like, you know, the person who left this DNA, what eye color do they have? What's their hair color? What are some of the features of their face? Can we start telling, you know, what racial group that they may have came from or where their ancestry is from? We can look at, you know, more paternity testing. We can start to look at mixtures of DNA, which are some of our more complex samples we get in a crime lab, and think about, are there better ways to deconvolute these with next-gen sequencing. So there's a whole host of things that we have started to explore that I think coming up in the next 5 years are going to become huge and are really going to open up a lot of what we can do in forensics with some of these samples that may have been sitting in our laboratory that we couldn't take through the traditional route.